Hi, I'm Mathieu from University of Rennes. I'm very happy to present the article Transfer Learning Across Variants and Versions, published at Transaction on Software Engineering, TSE in 2021. So this article is about a configurable software system, like the Linux kernel one. So such systems offer different configuration, either at compile time or runtime. So basically, the developers and users can set some options value, like Boolean 1, yes or no. You activate or deactivate some options, or you can set also some numerical values or string values. And once you have set a configuration, you can run it or build it, like in our case. So you use .configure and make, for instance, out of a .config file, and you get a new binary, which is here a kernel. And this variant, this kernel variant, has some property. So you're certainly interested by properties like performance, execution time, security, energy consumption, accuracy, etc. In our case, we are interested by binary size, so the size of the kernel binary. And of course, this size differs depending on configuration. So you can repeat the process, change some options value here and there, and you get a new kernel with different characteristics and different quantitative properties. So here the binary size is less than the previous example. And you can repeat again the process, right? On different configuration variants, and you get different quantitative properties. So an interesting challenge is to build a predictor, to a prediction model that will be able to take as input configuration, and without building the variant, will give you the quantitative property of interest, without, again, compiling and building it. And of course, this is changing, especially for the case of Linux, because the variant space is huge, and clearly you cannot enumerate all configuration at this scale. You can just consider a small sample, hopefully informative, so that you can infer interesting patterns out of it and predict in an accurate manner the binary size of a configuration file. But at the scale of Linux, that's really changing. Another challenge that is not really specific that is not specific of Linux, but that is exacerbated with Linux, is that Linux evolves a lot. It means there are lots of commits, modification of files, and there are also some additions and some removals of options. So the feature space is heterogeneous. It's not the same across version. And it's quite challenging for a predictor to first predict on a given version, but if the version changes and has impact on the binary size distribution, then that's basically the problem we are tackling here in this article. How to predict variability in space and time in an accurate manner and in a cost-effective manner, because building all this configuration is costly, of course. So basically for version 4.13, maybe we have put some efforts, we have invested some budget, we have a good prediction model, perhaps. And then 3 layers later, you want to reuse this prediction model, and maybe you have to do something because either the distribution is different or the feature space is different, has evolved. That's precisely the problem we are tackling in this paper. So instead of learning from scratch or reusing a prediction model as is, we propose to adapt a prediction model from one version to another. And one problem overlooked in the literature is that the feature space differs, it's heterogeneous, since options have been added or removed. So we propose a new technique called teams for transfer evolution aware model shiftings. And our key results are, first, there is indeed a rapid degradation of prediction models due to Linux kernel evolution, up to 32 prediction errors when you move from version 4.13 to version 5.8 3 years later. But this degradation can be managed through careful engineering and design of transfer learning teams, and we were able to reach the same accuracy 3 years later and outperform approaches of the related work. And yeah, transfer learning is possible, and it's quite a good news to that we show in these papers that we are capable of learning colossal configuration spaces such as the Linux kernel one across variants, but also across versions. Despite the heterogeneous evolution of the feature space. So now more details, of course, in the rest of the talk. So more details first about the Linux kernel. I have said that Linux offers lots of options, so 15,000 of options, and most of the options are three-state value, yes, no, or module. The rest is mostly Boolean, yes or no. And so if you look at the combinatorial, yeah, it's quite huge, right? So of course the number I'm giving here is another approximation because there are lots of logical constraints among options, but still it's just not possible at this scale to enumerate all configuration. You have to rely on a small sample. And the number of options continuously increases. For instance, between version 4.0 and 5.3, almost 3,000 of options have been added, which is a lot. So just to put perspective on this number again, the estimated number of atoms in the universe is much less than the number of variants of the Linux kernel. And yeah, we target the following case. We target the prediction of binary size because it's interesting for maintainers and users of the Linux kernel, especially people working on the IoT or embedded system or cloud-based technologies. And it's quite challenging to predict binary size, as I will show. So the first thing we did is that we measure lots of random configurations through the use of ranconfig. We choose version 4.13, which was in 2017, so now 5 years ago. And we measure such a huge amount of configuration. And an important number, I think, here is that a build of one configuration takes 8 minutes on average. So .configure make takes quite a lot of time, right? And so it has an impact, right, on our problem because it means it's very costly to gather all this amount of data. Not only due to the huge number of configuration, but also to the cost associated to each configuration. Another key number is the diversity of binary size numbers from 7 megabytes for the smallest kernel to almost 2 gigabytes. So lots of diversity. And the first question we ask is, do existing learning techniques work? Because most of the works in the literature consider a relatively low number of options, and Linux is quite extreme here. So we follow a classical methodology, classical process, which is based on sampling. So you select a subset of configuration, here through ranconfig. You measure by building some configuration, and you gather some variant. You can observe some properties like binary size, and then you can apply statistical learning, and there are many techniques out there. And then eventually you obtain a prediction model that you can somehow evaluate. So we did that with the use of Tuxml, which offers a reproducible environment with tools and packages written in Python to launch the procedures. And we have this dataset, right, in which each row is a configuration, and we have different metadata associated, like compilation time, binary size, etc., etc. So we did that for Linux 4.13, but for other versions we collect also many configuration. Details are in the paper. It takes 15k hours of computation on the green computing to gather the dataset of the version 4.13, which is a lot, right? And the first result is that basic linear regressions are not really working, even if you're shrinking the coefficients. Decision trees are quite okay, but the best learning technique is definitely gradient boosting tree. You can reach 6% if you invest some budget, like here, 90% of the whole dataset, which is basically 90k configuration, which is quite a lot. And also performance influence model and polynomial regression, when you're trying to capture feature interaction, are not able to scale due to the huge number of options of the Linux kernel. So binary size prediction is not straightforward at all. Some learning techniques do not scale, and if you want to reach a good accuracy, you need to invest and gather lots of configuration. But back to our core problem of the TSC article is that Linux evolves. There is this problem. So, okay, we have this prediction model for version 4.13, but what about other versions? And the first natural question we ask is, can we reuse the prediction model among versions? So we take the version 4.13 and we apply it to the other datasets. And we notice that the accuracy quickly decreases up to 35% for version 5.8. And even between version 4.13 and 4.15, so only two versions ahead, right? The increase is quite worthy, from 6% to 20%. So 4.15 is the spectrum meltdown version, but still it's the same for the other version, and the drop is the increase, is quite spectacular. So basically, we cannot reuse a prediction model. So should we put it in the trash? Well, that's quite sad, because we invest a lot of budget here to build it. So for tackling this problem, we propose to rely on transfer learning and to adapt transfer learning to the case of configurable system. And the specificity of our problem here is that the feature space is different. So transfer learning has been considered in the literature quite successfully, but not at the scale of Linux first, and also not for the case of heterogeneous transfer learning. So if you look at the dataset, you can observe that across versions, some features are added, but some features are also removed. So the feature space is not constant, right? And so you have to do something for making it work your prediction model, but also for adapting its efficiency. So first, you have to align the feature space. So we use a quite basic strategy in which we delete new features and we create dummy values for all features. So no complex mappings, but it was quite effective. And importantly, we designed an algorithm based on model shifting, in which the key idea is to learn the transfer function among the old size of the original version, of the source version, and the targeted version. And this transfer function can be linear in the ideal case, but we show that it's not sufficient, and you need to rely on more complex transfer function. And so we designed this algorithm, and thanks to that, also Teams is compositional. It means that you can combine transfer across successive versions. I won't detail this aspect in this talk. More details are in the article. Just to give you a glimpse of the behavior of Teams, so we have a source model. So for the source version 4.13, we use the predictor that has been trained on the source model, and we use this predictor across a new training dataset of the targeted version. So let's say version 5.8. We predict the size of the configuration. Of course, the prediction is certainly inaccurate because it is not suited for the version we tackle. But we can augment the dataset with useful information, and then the challenge is to learn the transfer function between the old size and the targeted size. And this is precisely what we did, and instead of using a linear relationship, we are considering gradient boosting tree algorithm here to learn the transfer function, which is then used to shift the model and to do the whole prediction. So is it effective? Yes. So the first important result is that, of course, we beat reuse. Reuse is when you blindly reuse a prediction model with as is. So I have shown previously that it degrades a lot in terms of accuracy. So Teams is able to beat reuse. Teams is beating also learning from scratch. So learning from scratch means that each time you target a version, you measure, you build plenty of configuration, and you try to build a learning model out of it. And Teams is outperforming learning from scratch. It means that it reaches better accuracy with the same budget. Of course, Teams needs a new training set to adapt the prediction model. And it's Teams is really effective for quite low budget. So for instance, when you have 1K configuration, model shifting is rapidly able to adapt the prediction model and reach quite good accuracy, while learning from scratch has difficulties because there are not that much configuration in the training set. It's simply not enough. If you increase the training set budget, learning from scratch, of course, improves, but still it's less than Teams. So Teams is effective, is beating another baseline, which is linear shifting, and we can reach almost the same accuracy 3 years later. So we have a tool called kpredict, and you can have a look. In conclusion, learning across variants and versions at the scale of Linux, we show that it's possible with careful engineering and transfer learning. Direct perspectives for Linux as future work is to consider more recent versions. Hopefully we won't observe negative transfer. Another perspective is to have a look at deep variability because we are considering the binary size, and maybe the consideration of another compiler like Clang instead of GC could alter our result, and it's worth looking at. And beyond binary size, our approach is really suited to target other quantitative properties like performance, energy, security, build time, etc. And beyond Linux, there are many configurable systems or software systems that have a huge variant space and that should vary in time due to continuous evolution. And we can ask the two key questions of the article. So thank you for listening, and I would like to thank very, very much my co-authors for this hard work. We spent lots of energy for gathering this amount of data and for carefully engineering an end-to-end solution with innovative learning techniques. And the preprint is available, and feel free to ask any questions. Thank you.